And we are back. Now remember, we had gotten to this point right here. We had just determined our formula to represent the volume of the sphere if it has been broken up into cylinders. Remember, the radius was the square root of 16 minus x squared. That's the height from here to here, if you will. The height was this width right here to some value x. Now what we're going to do is we're going to take this pi times 16 minus x squared x, and we're going to use our RAM program from -4 to 4. See, here's -4, over here's 4. And we're going to figure out, using the RAM program, what the combined volume would be if we use 25 cylinders versus 50 versus 100 versus 1,000. And then it says record only MRAM. The middle RAM, if you will, you see what the results will be from your calculator. 269, 268, and then on the way down to here. Now, let's compare that. Let's compare this estimate number right here using 1,000 cylinders. What would it be actually? Remember, the actual formula for volume is 4/3 pi r cubed. So we take our r and we plug it in, and if we work that out, 268.082, etc. And you see, now that's not exactly right, but that is a very, very, very good approximation, I think. I mean, you're accurate to what, 1, 2, 3 decimal places. That's a very good approximation. All right. Now, the last thing we want to talk about, and again, I will move the screen up so you can see, computing cardiac output from dye concentration. Now, again, ladies and gentlemen, if you are under the assumption that once you get out of my class, you're going into the medical field, perhaps you're going to be done with calculus, you need to think again. There's so much calculus in the medical field, and this is just one example, if you will. So here's what we have going on. An injection is made, a dye injection is made into a person, and from that dye concentration, they use it to measure circulation. So, for instance, after 5 seconds, the concentration is 0, 7 seconds, 3.8, and so on, etc., etc., etc. Then we take this data and we plot it. So at 5, we have 0, 5, 0. After 5 seconds, 0 dye concentration. And then 7, 3.8, 9, 8.0, and so on, and so on. So here's our graph. Now, we're going to use this graph to approximate the total cardiac output. Now, what that would essentially ask us to do is it's asking us to find the area underneath this curve. Now, what I have shown you thus far is a very analytic, numeric way to do this. And this is going to be the same, but it's also going to be a little more freelance. Here's what we're going to do. I'm going to take my intervals 5 to 7, 7 to 9, 9 to 11, and so on, and I'm going to draw my rectangles. And I'm doing, you see, the midpoint one here. I'm doing the MRAM, if you will, because you'll notice that the middle of each square roughly is, and then it should be exactly, it's just that's what I was shooting for, is roughly. The middle of each square or rectangle is what is touching the graph, so I'm doing an MRAM. Now here's where the freelance comes in. Notice I don't have an equation. You know, before we had the two endpoints that we would add up, divide by 2, get the midpoint, and we would plug that in. I don't have an equation on this one. So what I'm going to do now is I'm going to approximate the height. So what is the approximate height of this box right here? Maybe 1.5, possibly 1.3, 1.4. And then I'm going to approximate the height of this one up here, maybe 6.5 perhaps. And then I do that for all of the rectangles going through here. And this is what I have. Again, let me move the box down just a little bit. So again, for the first rectangle, I approximated a height of 1.4, then 6.3, 7.5, 4.8, all the way down to this last one over here that you can't hardly see, which is at 0.1. Now, where does the 2 come from? Well, remember, this represents all of the heights. The 2 would represent each of the widths, 5 to 7, 7 to 9, 9 to 11. Now, it could go 2 times that, 2 times that, 2 times that, you know, base times height, the base being 2 every time. Or I could simply factor out a common factor, if you will. I could pull that 2 out, and I could do this. When we work that out, 55.2 milligrams per liter per second, or 6.09 liters per minute. And that was the cardiac output. Alright, here's your homework. You can start on it now, or we'll work on it together in class. Make sure you come in with all kinds of questions if you have them. See you tomorrow.